Hello Jay, and welcome to my compiler's final presentation. The first thing that we're gonna go over is, so the first thing I did since the midterm was work on adding the assign homes to my X0 program. So, well, we can see what we did for a var when we got to assign it a home. So we would basically try to be filling out this var map and then be adding a key that assigns it to a register, and then we're going to replace the code with that register in like the instruction, like a move-q, etc. So we had this find next register function, which works kind of just works like stupidly, just scrolls through and assigns it a free register. But of course, we replaced this later and it didn't work that well. It was going to cause errors because the registers would fill up pretty quickly. It would fill up pretty quickly because we didn't have any sort of way to figure out like what the interference was between the registers. And then I tested this. Just random assign homes. So I think this test will currently pass because I decreased the depth of the program such that it wouldn't fill the registers. But let's just have it print the original. Actually, we probably want to print the S program and print the H program. And let's have this run 10 times so it doesn't blow up. All right. And let's move this onto the screen. Whoa. Oh, sorry about that. Okay. So I guess we can only scroll so far up. For some reason, this recording software only captures part of my screen. But we can see here, you might end up, so here's an original program. You see we have some var x, but then after the assign homes, now we have RSP. And there would also be a variable map that has the mapping of var x to RSP. So we were able to figure that out later. Okay, so the next thing, hello. The next thing that I added was the patch instructions pass. Okay, so I think I was a little bit confused about this one, which mentioned memory either 0 or 1 times. So this patch instructions. So here it is in the subtract q instruction. So for instance, if these were both like memory locations, we would add a temp register, and then we would add a move q and then a subtract q instruction. And then I also had some tests here where I was just running a bunch of random programs, and the patch instruction pass did not change the value of the program. So that was good. So next I had to work on my language runtime. So get that. Well, I emailed with you a bit about that, and that took some time to work out, but now I can figured out how to output programs, and I realized I was kind of outputting them pretty, like I was not outputting validly formatted or validly written programs, so I had to go back and change a lot of things in X0 with how I was emitting things. But now, see here, we have a nice test program that we can run that will just subtract 10. And then this is, this still isn't going to help me. So anyway, I would run my command to compile, and then I would test. And you're not going to be able to see this, but I'm going to enter 8, and it's going to return -2. And then we're going to scroll, push this up, so you can see that I entered 8, and then it returned -2, which is because it's just subtracting 10, which is what this test program is supposed to do. So I got that working, which was pretty cool. Of course, I did encounter the fact that Windows uses different color tape registers, so I had to use RCX instead of RDI. So that took some getting used to, but it is interesting to know these things for future reference. And I also had to do the function, use the helper.c to figure out what the main was, and then I also had my runtime.c was pretty much what you suggested in class. So there you can see those. So then the next step was working on Uncover Live. So for Uncover Live, this one was definitely presented an interesting programming problem. So I started with getting the live after, but if you see what we're doing here, we're actually going through the instructions in reverse and getting the live before, and then we reverse that list somewhat to get the live after. Okay, so for this live before, I was pretty much just using the algorithm that you showed us in class. So I can show you some examples where we found live, where we're doing live before. So this is live before for the add queue instruction. So I have this, some of this is just like this get var, this just gets, it gets the register name because basically I was storing it in a dictionary, and like if it's a variable or a register, those aren't hashable, so I had to do that. So yep, so that just gets the string so that it's easier to compare. So therefore we check if it's in none, or check if it's none because it's none if it's a constant or something that's not supposed to be something that's not something we care about as far as being live. And then if it's not in live, we will append it to live. And then that's pretty similar. And then for some, like this one for the move queue, we're removing var2 from live because it was not live until this thing was moved into it. So in that way, we're able to generate the lists of live things. So we had some tests for that in here. So we mostly were testing just by printing the program. So for instance, if I run this, I guess I can just drag the window up. That way you'd be able to see what it's doing. Okay. Yeah, I don't know why I didn't think of that before. Okay, so then we get some output here. Some of this is actually not what we wanted, but so here we have the live after each instruction. So move q1 to var x, live after is x. Move q2 to var y, our live after is y and x. Move q var x to var v, now we have y and v being live. No changes. And then we move v into rex, leaving just y live. And then, so actually the way it goes is it would just be this empty one, should be at the end here, but that's the general idea. So with that, yep. Try to make that big again. Okay, so that seemed to work to get our live before, live after, and yeah, and I was just storing just a list of, storing a list of lists of characters of the strings representing each variable. So the next step was the build interferences. So the build interferences is finding basically which variables interfered with each other, and then we base that off this live list that we would get from the live after. So we basically go through and pass each instruction its particular place on the live list that correlates with that instruction, and we calculate the build interference for that. So for instance, for here, I think this is a move Q instruction. So again, we get these strings, we make sure that var2 is not something we don't care about, and then like if it's a I think if it's, I think this might have been from something else, but yeah, so if var2 is not in this interference graph's keys, then we add it. So the graph will be mapping like a string representing a certain variable to a list of the things it interferes with. And then we go through this live list, and then we check if it is not already in the interference graph, and if it is not the same as var1 and var2, then we go through and append this into the interference graph. And then we also add its own entry, and then so it basically, if you have variables A and B, A will interfere with B, and B will also interfere with A, which is what this part is adding. So yeah, so we can look at some of the tests we did for that. Build interferences. Oh, we're still printing that. Yep, so we can run this. Let me move this up so you can see what's happening, and then let's run this guy. Let's close this window. Okay, so here we have our interference graph for this particular program I was using for testing. So X interferes with Y, Y interferes with XV, and RAX. V interferes with Y, RAX interferes with Y. And I also have to say this is a bug I just realized that I had. I was using RAX where I should have been using RCX as the variable that call Q. The variable that, or the register that call Q prints from. But ignoring that, you get the general idea. So next, I believe we were building the color graphs. So to do this, we're doing this all at the block level, I believe. So let's get down to that. Here we go. Here we have a color graph. So we would basically get a list of all the vertices in the graph, which are from the items in the interference list. Then we go through, we are, implementing this algorithm from the book. So exactly, I actually gave myself some comments here, which was nice. So so we're going through, we're starting, we're just default to the first vertex if we don't end up finding one that's more saturated. Otherwise, we go through and then we find the next most saturated vertex. And then saturated colors, we go through, we find all the adjacent colors that are saturated. We find all the colors of all the adjacent things on the graph because we know that we can't assign it a color that's in exact colors. So some of this is for the move by thing that I just added, but the other one is if we didn't have move biasing, we would just go straight into this, which basically goes through colors starting at 0 correspond to through the maximum, like the number of maximum keys or vertices. So we basically just find the lowest one that's not in the saturated colors. We choose that. And then, yeah, so we add that to our color graph. And then we remove it from our vertices. And then we loop through until we've removed every vertex and colored it. So let's print out some tests for our color graph. So actually I did a bunch of different ones. I think this one might have been from the textbook, so this might be interesting. Yeah, so this one has a ton of interferences, so let's see what it does when I run it, what it prints out. It should be this guy here. So yep, you can see it's able to use 3 colors to color this with all these interferences. Yeah, so I had a few different ones that I tested here, including the original program as well. All right, so then these once I had these, I could go through and then do the assign registers and assign and allocate the registers in a much better way than I was able to before. So, okay, assign registers. Where did we do that? So here we have assign and allocate registers. So to allocate registers, first when we're assigning registers, first we allocate a register. First we allocate registers. So the way we're doing that is we already have our color map, and then we're going to assign the colors to registers so that we can then use that map to assign all the registers. So what we're doing for this is there are the keys and values in this color map. So, and we're also checking to make sure I made a list of color registers, so we're just using those color saved registers, and then we check that it's not already been used, and then we assign it the first one in there that is not already being used for color. So yep, so and then next we go through this again. Oh, you know what this does? This checks to see if there's if you have any registers in this color graph. Like for instance, if before where we might have had RAX along with a variable name. So this would assign RAX to the first color. And then next we go and then assign the actual variables different colors. So we'll check what free registers we have, and then if there's any free registers, we'll assign that, and then else theoretically we would be did my headphones just turn off? Okay, apparently it's still recording. Sorry. Okay, so if the length of free is less than 0, sorry, I totally got thrown off. Okay, so and then here we have this theoretically we are implementing the stack here, but I didn't really go very deep into doing that. And then yep, so from assign registers, after we do that, now we go through each instruction and then call this assign register, and then basically just replace the variables with the new registers in the instruction list. And then some registers are getting deleted, so that's why we check delete the ones that say none. So my test for this, test assign registers. You can view the program before and after we run this, and also the bar map that's created. So here you can see we have bar X, bar Y, bar V. Then we get X, Y, and V are assigned to registers. And then we get this new program where that has all been replaced. Very nice. And then because at this point we could also run these new programs, I went back to my C0 test where I was doing testing on these randomly generated programs. Oh, the main generation pass. I don't think I talked about that. Yeah, this just tests so basically this just adds the HANA main and then moves this into the RCX so we can print it. Okay. So anyway, so we have a test for random assigned registers. However, here is where we ran into a problem. I suddenly found that once we were getting deeper than programs with depth 4, so in depth 5+, we started running into issues. So I tried a few things to try and figure this out. I tried setting the value that we were getting for when we did readint to 0 to see if that fixed the issue or help me isolate it. That didn't really help. And then we tried to color RAX differently because I worried there might be a problem with the coloring of that register, and that didn't really help me either. So if we run it with this depth of 4, it works fine. However, if we try to run it with a greater depth, like of 6, then that's when we start running into issues. But we might as well run this program now, so just so you can see what the current output is. So I did try debugging and looking at the programs that failed, but because they're all programs of depth 5 and 6, looking at them manually was it's pretty difficult to tell what was going on. And it wasn't like every program would fail, it'd just be every once in a while some would fail. And then I was trying to look at those programs and figure out why they were failing. And of course I couldn't set a breakpoint because I never knew when they were going to fail. It might run like 50 programs and then say that it fails. So I decided that I didn't really have time to figure that one out and decided I should just work on the next thing, which was adding this move biasing. Yeah, so that goes back to the color graph, and so I added an option for move biasing, and then basically it would then prioritize assigning it a color that was in this move graph that I created that basically said which variables were moved into other variables. And that was this like build move graph, which is just for the move queue. And yeah, pretty straightforward. It just is a dictionary from a variable to a list of variables it is moved into. All right. And so I created a test for that. But the problem with that is, even though I used kind of the one from the textbook, my algorithm just worked a little differently, so it didn't actually really make a difference. And then I tried assigning like defaulting like x to be 1 in the dictionary, because here you can see, okay, here you can see this is without move biasing, and then this is with move biasing, and it's actually, it was the same, but now it actually ends up just swapping 0 and 1. So it essentially is the same as it was before. But you mentioned in your email that this, especially if you do the RCO pass the way you said, which I did, that this won't actually be relevant to a lot of programs. So I'm just going to leave this for now. And so that was about as far as I got on this project. I did really enjoy this class. I feel like I learned a ton of interesting things and definitely have a deeper understanding of how compilers work, and it is pretty cool, even though I didn't exactly get like a fully working beautiful end-to-end compiler, that I still did learn a lot from what I did. So yeah, so one of the things that I liked about this project is it gave me a lot of interesting programming challenges, because basically having to implement all these different little languages and all the passes, and I enjoyed the challenge that gave me, adding those, sorry. So yeah, so I definitely found this was an interesting programming challenge. Yeah, so I definitely, there were like a lot of times where I was like, oh, I should refactor this. Why did I do this way, one time, and then like another way the other time? So that was something that like I definitely would think about in the future, or try and get more of an overarching kind of design idea for what I was doing. But I feel like I kind of didn't know what I was doing, and then I slowly figured out what I was doing, and then like I figured out a way to do it, and I was just trying to do it as fast as possible. So yeah, so I think that shows some of my code is a little sloppy, and also I should have left a lot more comments, because sometimes I'd be like, what am I doing here? Like, what was I thinking? And so yeah. But I did really, I don't know, I really did enjoy working on this class, even though it was at times quite stressful. So I think I mentioned this before, but one thing I did find kind of stressful was the fact that there were so many individual tasks to complete. I do feel like some of the tasks could have been squished down to one, like a couple instructions could be switched down to one, and then yeah, that might make it feel less daunting. And then I felt like once I got behind, I was just got like so far behind that it just seemed impossible for me to ever catch up. And I do feel like I feel bad for missing class today, and I feel bad for like not having been as focused in the past few classes, as I have been trying to work on this in class while also trying to pay attention to your lecture. However, that is very difficult to do. So I do think, I mean, I guess I can still go and watch your lectures online, but I think the stuff you're talking about is really interesting, but I also feel like it's hard for me to, like, knowing that the stuff in class is not going to ever, like, it's not going to actually, I'm not going to actually end up using it on my compiler, so it's hard for me to, like, prioritize it in that context. But yeah, I really appreciate that you offered this class. I think it definitely was unique compared to a lot of other classes that I've taken at Lowell, and I thought that was pretty, it was pretty cool, and I think you have, like, you know a lot, so it's cool to hear you talk about subjects that you're passionate about and stuff like that, and, like, yeah. And I appreciate that you've been a helpful and supportive professor. So I'm gonna send you, I'm gonna zip up all my code and my commits and send that to you. So thank you very much. Like, comment, and subscribe.